Hello students, welcome to the session of normed linear spaces. So I would like to define what is a norm on a linear space. So the word norm is a function. It is a kind of function defined on a linear space. Okay, so norm only can defined on a linear space, right? So what is the definition of normed linear space? So for that, first we need a linear space. So let X be a linear space. Linear space. Okay. Comma. Okay. So we have a linear space X. Then norm is a real valued function. What is a norm? A norm is a real valued function. Real valued function which is denoted by two parallel straight lines. This is called a norm. Okay. On X. It is called a norm only if satisfies the following conditions. The conditions are for every f, g in X and alpha belongs to R, where R is a corresponding scalar field. Okay. The first condition says norm of is greater than or equal to 0 and norm of equal to 0 if and only if f equal to 0. And this condition is called non-negativity condition, which is also same as in the case of metric space. Second one, these properties are almost same as in the metric space. Second one, norm of alpha f is equal to mod alpha into norm f, where alpha is a scalar and f is an element in X. That means it is a vector. And this condition is called positive homogeneity. And third one, our famous triangle inequality. So all these properties are satisfied under this function norm, which is called a norm. And what is this norm? So I can say that this norm is a mapping from X to R because it is a real valued function, right? It is a real valued function. What is X? X is a vector space. X is a linear space over R. Linear space over R. Okay. So when you have a function f which is a mapping from a vector space v1 into vector space v2 such that f of x1 comma or f of x1 plus b x2 equal to f of x1 plus b into f of x2. These functions are called actually linear transformations. Linear transformations. I think you all know this. What are linear transformations? This is a mapping from a vector space into another vector space which keeping the linearity property. Okay. So what is a linear functional? When you have a function which is a mapping from a vector space into a scalar field, right? It's a scale from X to a scalar field which is also linear, which is called a linear functional. So when a map is from a vector space into its corresponding scalar field, we call that function as a functional, right? Functional. So I can say that here norm is a mapping from, which is actually a real valued function on X. So it is a mapping from X to R, where X is a linear space over R. So it is a mapping from X to its corresponding field. So I can say this norm is a functional. So I rewrite it is a real valued functional because it is a mapping from X to its corresponding scalar field. Okay. So norm is a real valued functional which satisfies all the three conditions. Then we say that X together with this norm is called normed linear space. X together with a matrix called metric space. X together with a topology is called a topological space. Then X together with this norm is called a normed linear space, where provided X is a normed linear space, right? So it is called a normed linear space. I write NL space, normed linear space. Okay. So this is the basic definition of normed linear space. But in this section we are discussing on the capital LP and L infinity spaces, right? We are discussing on capital LP spaces, measurable functions with integral over E What are LP of E? LPO equal to measurable functions. Measurable functions such that integral over E mod f raised to p finite. And what is L infinity of E? Measurable functions such that they are essentially bounded. Essentially bounded. So we are considering about these kind of functions, these kind of spaces. Now we are going to prove that a proposition which says our capital L1 of E is a normed linear space. Normed linear space. Under the norm is defined as actually norm f equal to integral over E mod f. And this norm is denoted by one norm, okay? Instead of norm, I write one norm because it is a norm on L1. Okay, to understand that, we denote it as one norm. One norm of f is equal to integral over E mod f. And I will prove that this one norm is a norm on L1 of E. What is L1 of E? L1 of E is nothing but, we know what is L1 of E. It is set of all measurable functions on a measurable set E, measurable set E such that integral over E, LP says that integral over E mod f raised to p finite. Here mod f raised to p means p is 1, right? P is 1 means mod f raised to 1 is finite, which means integral over E mod f is finite. What is the meaning of integral over E mod f is finite? Means mod f is integrable. That is the meanings. Mod f is integrable. We know a function is integrable, a modulus of a function is integrable only when f is integrable. So which means f is integrable. So I can say that what are L1 of E? L1 of E is nothing but set of all measurable functions whose modulus are integrable, or in particular that functions are integrable on E. Right. So what are the examples? What are the elements in this collection? If you want to say one element in this collection, you can say an example of an integrable function on E. Okay. So what is L1? L1 of closed interval AB. Instead of E, I write a closed interval AB. You know closed interval AB is a measurable function whose measure is nothing but its length. So instead of E, I can consider closed interval AB. So what is L1 of closed interval AB? Set of all integrable functions. Actually, modulus of f is integrable on closed interval AB. So you can give infinite or plenty of examples which are examples of functions which are integrable on closed interval AB. Right? Every continuous function or any constant functions. So that's our elements of this L1 of closed interval AB. So any continuous function defined on E, any constant function defined on E are the elements of L1 of E. Okay. So now we are going to prove this theorem, this proposition. L1 of E is a normed linear space under the one norm. One norm is defined by, we have to remember this formula. One norm of f is equal to integral over E mod f. So how will you prove this proposition? So we need to prove L1 of E is a normed linear space under one norm. What is one norm? One norm of f is equal to integral over E mod f. Okay. So we need to verify all three axioms of normed linear space: non-negativity, positive homogeneity, and triangle inequality. So for the first one, non-negativity. So I take let f is an element from L1 of E. Okay. Since it is an element in L1 of E, which implies I can write integral over E mod f will be finite. Finite means which implies mod f is integrable over E. Integrable on E. Okay. We need to prove that one norm is positive. What is one norm? By definition, one norm of f is equal to integral over E mod f. Right? So what is mod f? Mod f is always positive, right? Since mod f is always positive, implies integral over E mod f will be always positive. So which implies one norm of f is always positive. Okay. So what will be this is 0? If one norm of f is equal to 0, then Integral over E mod f is equal to 0. Integral of a function is equal to 0. Lebesgue integral of a function is 0 implies mod f must be equal to 0. Actually, if and only if. If and only if mod f is equal to 0 almost everywhere on E. Which is if and only if f equal to 0 almost everywhere on E. Right? So which satisfies the first axiom, non-negativity. Therefore, non-negativity condition will be true. Non-negativity is true. For the second one, this is first one. Second one, what is positive homogeneity? That is, we want alpha norm of 1 norm of alpha f is equal to mod alpha into 1 norm of f. This is we need to verify. So for that, I take let alpha belongs to R and f belongs to L1 of E. Okay. Then what will be 1 norm of alpha f, which is equal to, by definition, integral over E mod alpha f. When 1 norm of f is equal to integral over E mod f, 1 norm of alpha f will be integral over E mod alpha f. And this is equal to mod alpha can be taken outside in the property of Lebesgue integral. So mod alpha into integral over E mod f. And what is this? Mod alpha into integral over E mod f is denoted by 1 norm of f. So which easily can be proved. What about the third one? Third one is triangle inequality. So for that we need to verify 1 norm of f plus g equal to, less than or equal to 1 norm of f plus 1 norm of g. Okay. So consider 1 norm of f plus g, which is equal to, by definition, integral over E mod f plus g. So this is nothing but less than or equal to integral over E mod f plus integral over E mod g, right? So this is equal to 1 norm of f plus 1 norm of g. So which will be trivial. So we proved all the axioms of normed linear spaces. Therefore, L1 of E is a normed linear space over R. Next, we will prove that one more proposition. Our L infinity of E, our space L infinity of E, is also a normed linear space. Is a normed linear space over R under the norm norm f equal to essential supremum of f over E. Okay, and this norm is denoted by subnorm, essential subnorm, and which is denoted by infinity norm. Okay, and we need to prove that which also satisfies all the three axioms of normed linear space. Okay, so for the non-negativity condition, I take let f belongs to L infinity of E. Then you know f belongs to L infinity of E means f is essentially bounded on E. Essentially bounded on E. Or there exists m greater than or equal to 0 such that modulus of f of x is less than or equal to m almost everywhere on E. So this is by definition. We need to prove first to verify the non-negativity condition. So what is infinity norm of f or essential supremum norm? This norm is called essential supremum norm. Okay, so essential supremum norm of f is defined as essential supremum over f, since what is this, and which is denoted by actually essential supremum of mod f. Okay, essential supremum of mod f. Okay, so mod f is always a positive number, then essential supremum of mod f will be always positive, right? So therefore I can say that this will be always greater than or equal to 0. Okay, since mod f is positive, and if now if subnorm of f is equal to 0 implies essential supremum of mod f is equal to 0. So which means whenever essential supremum of mod f is equal to 0 means actually mod f is equal to 0. Mod f is equal to 0 almost everywhere on E. Okay, then f is equal to 0 almost everywhere on E. So which is actually if and only if condition. So the converse part can be proved easily by using mod f is equal to 0 if and only if f is equal to 0. Okay. For the positive homogeneity, you consider let alpha belongs to real number and f belongs to L infinity of E. Now consider subnorm of alpha f. By definition, it is essential supremum of mod alpha f. Okay. So essential supremum of mod alpha f. This can be written essential supremum of mod alpha into mod f, which is nothing but mod alpha can be taken outside essential supremum of mod f. Okay. So that is equal to mod alpha into essential supremum of mod f is denoted by subnorm of infinity norm of f. So you get infinity norm of alpha f is equal to mod alpha into norm f. So which satisfies the positive homogeneity condition. Now for the triangle inequality, I take two elements f comma g belongs to L infinity of E. We want to prove that norm of f plus g less than or equal to norm f plus norm g, right? So since f and g belongs to L infinity of E, so let f comma g belongs to L infinity of E. Then you consider f plus g, norm f plus g, which is equal to by definition integral over E modulus of f plus g. Essential supremum. Okay, since the space is L infinity, essential supremum of mod f plus g. And you can prove that essential supremum of mod f plus g will be less than or equal to essential supremum of mod f plus essential supremum of mod g. Okay, and essential supremum of mod f is denoted by norm of f, and essential supremum of mod g is denoted by norm g. Okay, so you get norm of f plus g will be less than or equal to norm f plus norm g. So triangle inequality will be true. Therefore, L infinity of E is a normed linear space over R.